Okay, so we're going to get into the properties of parallelograms and special parallelograms. So a parallelogram, just so we can recall, is a quadrilateral where both pairs of opposite sides are parallel to each other. Okay, so we're going to get a quick theorem about this. The quick theorem here is that it's going to be, if I have a parallelogram, the opposite sides of a parallelogram are not only parallel, but they are congruent. Okay, so we're going to prove this, that the opposite sides of the parallelogram are in fact congruent. Okay, so let's start with a little drawing here. We're going to make a parallelogram to work with. We'll put it up here. We're going to call this H, G, E, and F. All right, so we're going to be given that E, F, G, H is a parallelogram, and we want to prove ultimately that EF is congruent to HG, and we want to prove that FG is congruent to EH. Okay, so statements, and we have reasons. All right, so the first thing is that we know that EFGH is a parallelogram. How do I know this? Because we're given it. Because they told us so. Alright, so right off the bat, that tells me that HG is parallel to EF, and HE is parallel to GF, because that's what it means to be a parallelogram. So that's the definition of a parallelogram. Alright. So we just established that this is parallel to this, and this is parallel to that. All right, so we're going to build a segment in here. We're going to build a segment GE, right? And I can construct that because any 2 points are going to determine a line. And this is going to be number 1, angle 2, angle 3, and angle 4. So that line that I just constructed happens to form a transversal. Now, if these two are parallel, that means angle 1 and angle 2 have to be congruent, right? Because these are alternate interior angles. It also means that if these two are parallel, 3 and 4 have to be congruent. So angle 3 also has to be congruent to angle 4. This is all because these are alternate interior angles, and by the alternate interior angle theorem, those angles have to be congruent. Okay, so this segment GE has to be congruent to itself. That's the reflexive property. Well, I just made two congruent triangles. I got the triangle EGH is congruent to triangle, so EGH has to be congruent to triangle GEF, and that's because they both have an angle aside, right? That one, and an angle, so that's angle side angle. And the whole point of proving that these are congruent is now their corresponding parts. HG has to be congruent to EF, and HE has to be congruent to GF. So FG has to be congruent to EH, I think is the way we originally said it, and that's because the corresponding parts of congruent triangles are congruent, CPCTC. So we've now established that the opposite sides of a parallelogram have to be congruent. Now, if you pay really close attention here, you can see that H up here is a corresponding part to F, which means that these opposite angles must be congruent. Now, had I done this whole proof and drawn the other diagonal in, I would be getting that G and E are congruent. So what we've just established there, without any additional proof, is that the opposite angles of a parallelogram are also congruent. So I've got a couple of things that I've said right off the bat. The opposite sides of a parallelogram are congruent. And without any additional proof, I got that the opposite angles of a parallelogram are in fact congruent. Okay, the third statement that I'm going to make here, and it's pretty similar, is that the diagonals of a parallelogram bisect each other. Okay, so that's pretty significant. The diagonals of a parallelogram have to bisect each other. So we're going to take a minute, we're going to prove that. This takes a little bit of thinking again to prove this. Okay, so let's again start with a drawing. We're going to use a very similar drawing to the last one. Okay, so there's a drawing. We'll call this TSRQ. We're going to put in both diagonals. We'll call this point M. I'm going to label some angles. We'll call this one angle 1, angle 2, angle 3, and angle 4. And what we want to do is, if we're given this parallelogram, let's call it QRST, we want to show, so prove that QS and TR bisect each other. All right, so we're going to again need statements and reasons. And right off the bat, we get that QRST is a parallelogram. And I'm given that. All right, that's great. We just proved, all right, since it is a parallelogram, we actually know that TS has to be parallel to QR. That's by the definition of a parallelogram. So TS has to be parallel to QR. All right, so if these are parallel, that makes 1 and 2 alternate interior angles, makes 3 and 4 alternate interior angles, so 1 has to be congruent to 2, 3 has to be congruent to 4. It's by the alternate interior angles theorem. It's almost like we've played this game before. We also happen to know that TS is congruent to QR because we just proved that the opposite sides of a parallelogram are congruent. So not only are these things parallel, but they're also congruent. This is going to get me that triangle TSM, the top triangle up here, is congruent to triangle RMQ, and TSM, sorry, it should be RQM, and that's now by, let's see, angle, side, angle, angle, side, angle, that's angle, side, angle. Okay, so note what we just proved is that these two triangles are congruent. So hold on to that dot, and we're going to make some more space. Okay, so we've just made a little bit more space in our proof here. Our last thought was that these two triangles were congruent. So what I can now say is that QM is in one of these triangles, it's congruent to MS in the other, and TM is in the one triangle, and it has to be congruent to MR in the other, and that's by CPCTC because these are corresponding parts, which means that if this is equal to that, then TR bisects QS, and if this is equal to that, then QS bisects TR, so we can affirmatively say that QS and TR bisect each other, and that's because that's what a bisector is. It's something that cuts something else into two equal parts. So definition of a bisector. Alright, so we have now gotten 3 facts about parallelograms. Their opposite sides are congruent. Their opposite angles are congruent. And their diagonals bisect each other. Okay, we have a couple of special types of parallelograms. One is a rectangle. And a rectangle is simply a parallelogram that has 4 right angles. This is easy to remember because rect is actually like the German word for right and angle. So the word rectangle actually means right angle. If I have a rhombus, it is also a parallelogram, but a rhombus has all 4 sides are congruent. So the rectangle has 4 congruent angles, the rhombus has 4 congruent sides. If a rhombus and a rectangle have a baby, they are going to be a square. Okay, so a square is the combination of the two. It has 4 right angles, and it has 4 congruent sides. So these are our special types of parallelograms. So we're going to get some properties from this. The first one is that if I have a rectangle and I measure its 2 diagonals, we're going to say that these diagonals are congruent. So let's prove that. Let's call this A, B, C, D. We're going to be given that A, B, DC is a rectangle, and we want to prove that AD is congruent to BC. Alright, so there's my statements. Here's my reasons. Let's see if we can do this. Okay, so we're given that ABDC is a rectangle. Okay, that's pretty straightforward. That's what we're given. Okay, so because a rectangle is a parallelogram, we know that AB has to be congruent to CD because the opposite sides of a parallelogram are congruent. So that has to be congruent to that. Moments ago, we proved that the opposite sides have to be congruent. We also know that the measure of angle BAC has to equal 90, and the measure of angle DCA also has to equal 90, because that's the definition of a rectangle. It has to have 4 right angles. So we know that this is a right angle and that's a right angle. I also know that segment AC is congruent to itself. It's by the reflexive property. Okay, so now if I take a look at this in the right lens, I'm going to draw 2 triangles here. Okay. I have a triangle ABC, that guy there. I have another triangle, CDA, that guy there. Okay, so they have a congruent side and a congruent side. They have a congruent angle and a congruent angle. And then they have a side in common, which is congruent to both. So these two triangles are in fact congruent. So we know that triangle BAC has to be congruent to triangle DCA. And this is by SAS. Okay, well, one diagonal is in one triangle, the other diagonal is in the other. So this tells me that BC has to be congruent to AD by CPCTC. And I've proven that the diagonals of a rectangle must in fact be congruent. Alright, so what can we say about a rhombus? Okay, well, we can say a couple things about a rhombus. So let's take a look at that. Okay, so let's start off by saying I have a rhombus, right? And I'm going to call this A, B, C, D, and I'm going to draw in its diagonals, right? In its diagonals. We'll call that point in the middle M. And the conclusion that we'd like to draw is that these diagonals are definitely not the same length. I mean, like this one's shorter than that one. But that the diagonals, in fact, are perpendicular. So if I'm given rhombus ABCD, right? We'll call it ABCD. We want to prove that line AC is perpendicular to segment BD. Segment AC is perpendicular to segment BD. This is actually quite a simple proof. You don't have to do a whole lot of thinking here. So if I have rhombus ABCD, that's given to me, right? Then I know the following things are true. AB has to be congruent to BC, and AD has to be congruent to DC. So this must be congruent to that. That must be congruent to that. In fact, it's pretty straightforward that that's the case. Now, so that's by the definition of a rhombus. Okay, so this is specific to a rhombus. All right, so what do I know? I now know that B is the same distance from AC, right? I also know that D is the same distance from AC. This means that both B and D are on the perpendicular bisector of segment AC, because points that are equally distant from the end points of a segment lie on its perpendicular bisector. Okay, so this was like something that we proved, like the converse of the perpendicular bisector theorem, something that we proved last time around. Well, if these things are on the perpendicular bisector, that means BD is the perpendicular bisector, which means, in fact, BD must be perpendicular to AC. BD has to be perpendicular to AC, because that's by the definition of a perpendicular bisector, is that if it's going to be a perpendicular bisector, it has to be perpendicular. All right, so that proves that the two diagonals of a rhombus are perpendicular. Okay, so we've got one last fact about a rhombus that we need to be able to say, is that the rhombus's diagonals actually bisect the exterior angles. Okay, so what are we saying here? We're saying that if I have a rhombus, right, so here's my rhombus again, we'll call it again A, B, C, D, and we're going to draw in these diagonals. We'll call this point M. We're saying that BD bisects both angle B and angle D, and M bisects angle A and angle C. So we're going to be given nothing more than a rhombus. ABCD is a rhombus. Okay, what do we want to prove? We want to prove, so without loss of generality, I'm just going to prove that BD bisects angles ABC and angle ADC. Like if I can do it left to right, that means I can do it up to down, so I don't have to prove it both ways. Should suffice to show this. You should be able to follow the exact same proof and get the one that goes the other way. So let's start with ABCD is a rhombus. How do I know this? Because it's given to me. Okay, that's the big given fact. Alright, so from that, I'm going to do something here. AB has to be congruent to BC. Okay, so AB is congruent to BC. And in fact, AD is congruent to CD. So AD is congruent to CD. Why is this? Because this is the definition of a rhombus. Okay, that all the sides have to be congruent. Okay, we also know that BD has to be congruent to itself. It's by the reflexive property. Okay, so this guy is congruent to itself. Well, there we go. We got two congruent triangles, right? The one up top and the one on the bottom. Triangle ABD has to be congruent to triangle CBD because of SSS. Okay, so that means a bunch of stuff's happening here. Angle ABM has to be congruent to angle CBM, and angle CDM has to be congruent to angle ADM. And that's by CPC, TC, because this is part of the top triangle congruent to the bottom, part of the top triangle congruent to the bottom. Well, if this segment is busting these into congruent angles, that means that segment BD bisects angle ABC and angle ADC, because that's the definition of an angle bisector. Okay, so just kind of recapping here. If you have a parallelogram, then the opposite sides are congruent, the opposite angles are congruent, and the diagonals bisect each other. A rectangle is a parallelogram with 4 right angles. A rhombus is a parallelogram with 4 congruent sides. A square is a parallelogram with 4 right angles and 4 congruent sides. If I have a rectangle, the diagonals are congruent. If I have a rhombus, the diagonals are perpendicular, and they intersect the opposite angles in such a way that they actually bisect those angles. Alright, so there's properties of parallelograms and special parallelograms.